Hello grade 12s. This particular video just covers differentiation, more past paper examples. So in this entire video, we're just going to use that differentiation rules that I discussed in the previous video to find the derivatives of all of these particular functions. So you'll see I tried to select as many different ones as possible, just so you get like huge variation on this. And I also got some tricky ones, so shout out to Josh. We are going to follow the Josh method here, saying, okay, I get this, but how can they complicate this? So I tried to leave those answers to the end of the video, so we can start first just building up the basics, and then at the end we can look at some tricky examples that have been asked in past papers. So I did state this in the previous video. A lot of the effort with finding the derivatives of these functions is not actually using the differentiation rules. It is prepping the algebra so you can use the differentiation rules. So in this particular case, we're going to write down y is equal to. And you will notice right there, I have a surd or I have a root. I'm just going to remove this because currently it's shining through. So I think it's going to be easier if I just do it like this. So currently I've got a surd over there, which I'm going to have to write down as a rational exponent. So that's going to be my first job, saying it's x to the power of 3 plus x to the power of, now be very careful here. There, even though it isn't stated, is a little 2 because this is a square root. So that's going to be x to the power of 3 over 2. That's my rational exponent. And then this, I just put x down. Now, I've now taken care of the surd. That was the first problem. But the second problem is this is a quotient. It's the top divided by the bottom. And we've spoken about that also in the previous video. I cannot go and use my differentiation rules if there's a product, or in this case, if there's a quotient. So in order to simplify this one, I go and I use what we call the Distributive Law of Fractions. Now, this was taught to you in grade 8, believe it or not, which says you can go and you can use x to the power of 3 divided by x plus x to the power of 3 over 2 divided by x. And the reason you're allowed to do that, if I can write it out just on the side so you can see, is because we are saying it's x to the power of 3 plus x to the power of 3 over 2 divided by that denominator, which is x. Which means I can divide it distributively. I can say it's the first term in the numerator divided by the denominator plus the second term in that numerator divided by the denominator. So that's why I can split it up like this. So then I can go and I can simplify saying this is x to the power of 2 plus x to the power of, careful, 3 over 2 minus 1, because obviously this is division of powers. And if I do division of powers, I go and I say it's the top exponent minus the bottom exponent. So that's why it's 3 over 2 minus 1, which is a half. Now it's in a format where I can find dy over dx. So all of this, people, again, look at your notation, is still y. And the reason it's y is because I haven't used any of the differentiation rules. I've just used algebra to simplify this. But now that I'm ready, I can go dy over dx is equal to 2 times 1, which is 2, x to the power of, make that exponent 1 less, which is 1, plus half times 1, so that's a half, x to the power of, make that exponent 1 less, so careful, a half minus 1 is negative a half. And just because we're trying to practice these good habits, I am going to go and I'm going to change that negative exponent into a positive exponent, saying 2x to the power of a half. Just a good habit, especially if they state changing all the negative exponents into positive exponents. Now the next is also from that 2019 paper, and they asked you determine the derivative of that function inside the bracket in terms of x. So there again is one of our notations that we have discussed in one of the previous videos. Now, in order to simplify this, you need to be very careful because right there was the big trick in this particular one, that negative 1. So what a lot of people didn't realize is you had to go and you had to rewrite this. And when they rewrote this, you had to write it in the format 8x cubed minus 27 divided by that 4x squared plus 6x plus 9. And that's simply because we've already discussed it. A negative exponent means this entire bracket, because the negative exponent is applicable to the entire bracket. That whole bracket is on the wrong side. It's currently in the numerator. It needs to move into the denominator, and then I can change the exponent from negative to positive. Now, this is also like one of the previous examples we've discussed, where it said I cannot find the derivative if I have a quotient. And remember, I wrote that down if, people. Normally, if I want to simplify fractions, first factorize fractions. So I'm still writing that dx. Watch your notation. And the reason I'm still writing this dx is I cannot drop that dx notation until I'm ready to find the derivative. So as long as I'm simplifying this function, I have to rewrite that dx again and again and again. I know it's annoying, but sorry, that's just the rules. Now, this is the difference of cubic numbers. And you might have forgotten how to factorize these. That is grade 10 mathematics, so you might want to just go and check how to factorize these cubics. So in order to factorize this one, we're going to go and say the cube root of 8x cubed is 2x. The cube root of negative 27 is negative 3. And then I know that it's going to have to be a binomial times a trinomial. And to get that trinomial, I square the first term, which is 4x squared. I square the last term, which is plus 9. But here's the only tricky bit. I have to multiply these two terms and change the sign. So it's going to be plus 6x. So there you go. 8x cubed minus 27 is 2x minus 3 times 4x squared plus 6x plus 9. Now that's trinomial, so I factorize the trinomial. And when I factorize the trinomial, I realize suddenly something. Hang on, do I really need to factorize that trinomial? Because look at that. This seems incredibly familiar. So no, I was not supposed to factorize that trinomial. Besides, if you had tried to factorize that trinomial, you would have spotted that you can't actually factorize it. Because hopefully from grade 10 mathematics, you will remember that when I factorize the difference of or sum of cubic numbers, that trinomial I get will never be able to be factorized. So that is why, logically speaking, I did need that 4x squared plus 6x plus 9, 6x plus 9 to be divided into that particular factor at the top. And then suddenly you realize that this question actually wasn't a difficult differentiation question, it was more difficult algebraic simplification question. Because once the algebra has been simplified, and please see I'm still writing the dx there, because now I know that simplified that expression is 2x minus 3. And now only am I ready to employ the differentiation rules. So the moment I'm ready to employ the differentiation rules, I can just write equal and I can say the derivative of 2x is 2. And I discussed how you can easily just go and spot the derivative of that linear term is just equal to 2. And please again remember the derivative of a constant is 0. So after all that, the derivative is just simply 2. Okay, continuing with the next example. And the next example is from the Department of Basic Education, and this was their November 2019 paper 1. So in this particular example, they said, determine dy over dx if y is equal to 4x to the power of 8 plus x to the power of 3 underneath the square root. Now we've done one like this before, but I just thought let's practice this again because some of you guys do struggle with these rational exponents. So because it's a square root, I'm going to put a little 2 over there just so you remember square root has a little 2. It's still y equal to, because I'm prepping this before I can employ the differentiation rules. And that's going to be 4x to the power of 8 plus x to the power of 3 over 2. So there's my rational exponent. Now I can go and I can say dy over dx is equal to, because I'm ready to use the differentiation rules, 8 times 4 is 32. X to the power of, make that exponent only one less, so that's 7. Plus x to the power of, and make that exponent one less as well, so that's 3 over 2 minus 1. But if it's 3 over 2 minus 1, it's 3 over 2 minus 2 over 2, which is a half. And that's then the derivative of that function. Then, in that same paper, they had question 7.3, where they said, given that y is equal to ax squared plus a. Now, this one is one of those ones that I said, we're going to do the Josh method. Like, okay, I'm kind of understanding what's going on at the moment, but how can they go and they can complicate it? Now the first one is not that complicated, but this one you'll see something very interesting happening just now. But let's first discuss this one. So please people remember, whenever you're trying to find the derivative, they will state here at the bottom, right here, they're telling you the independent variable in this case is x. So in this case, x right there is my independent variable. Any other variables that appear, we will treat like constant values. So we're just going to write this down because they say dy over dx, x is my independent variable, and a is going to be therefore be a constant. So any other variables now become constant values. So this one's already prepped. I don't have to prep it. There are no fractions with x underneath the fraction in the denominator. There's not a product. There are no quotients. There's nothing that needs to be simplified. So at least the algebra there is very easy. So I'm going to go straight into finding dy over dx. So I write dy over dx is equal to. So because this is a constant, I consider that to be the coefficient of x squared. So I go 2 times a, x to the power of, make that one less. So that's 2a x to the power of 1. And when I get to this one, careful people, because I did tell you guys, because x is the independent variable, a is the constant. So the derivative of a constant is 0. So that's the answer to this particular question. I'm done. But now what they've done is they've complicated it. And a lot of people didn't even spot this question. They didn't even spot that suddenly x is no longer the independent variable because they want you to find the derivative of the function y in terms of a. So right over there, they've said we're now changing things up. So because a in this case is now considered my independent variable, which means I need to find the derivative in terms of a, x is now considered my constant. So this one becomes quite tricky. So if I go back to this one again, and I want to find the derivative of y in terms of a, I need to understand, and I can actually even swap these around. So if you do want to quickly just swap them around and you want to say, so y is equal to x squared times a plus a, just to help you a little bit, because like I said, a is the independent variable, x is the constant. Then the variable I'm using there is a, so my exponent is 1. So I'm going to go and say it's 1 times x squared, because that entire x squared is now my coefficient. So 1 times x squared is x squared. But when I find the derivative of that a to the power of 1, which means I have to subtract 1 there, and I write it down just for you guys to see, I've got a to the power of 1 minus 1, which is 0. And then be very careful over there, because like I said, a is now the independent variable. So there's a little 1 there as well. And I will also write this down so you guys can see it. I'm going to go and say 1 times 1 is 1. And then that's going to be a to the power of 1 minus 1, which is also 0. Now obviously you didn't have to do this, but I'm just showing you guys how this plays out. So you can see every single step. And that is why a to the power of 0 is 1. So x squared times 1 is x squared. And a to the power of 0 is 1, so 1 times 1 is 1. And just by changing this notation a little bit, we had to go and understand that it's no longer x that's the independent variable and a that's the constant over here. In this case, a is the independent variable and x is the constant. So yes, this one was quite a nice tricky question. So shout out to Josh, this is how they can complicate it. Okay, next example is from the IEB March 2019 paper. So this was the 2019 supplementary paper 1. Now this is back to again something fairly straightforward and easy. We have encountered these ones before. So I'm going to go quite quickly through this one. Again, this is still y. I'm not going to write dy over dx there because I can't use the differentiation rules yet, not when I have that surd. So that's going to be x to the power of 2 over 3 plus 3x squared minus 4x. Now, please note, people, you can't go and find the derivatives in batches. I've seen a lot of people go and they first write this one as x to the power of 2 over 3, which isn't the derivative. It's just simplifying or putting that surd into rational exponent form. And then I have people who go and say, oh, but this is easy. If I find the derivative of 3x squared, it's 6x. So suddenly over here, 6x will pop up. People, you cannot find derivatives in batches. You can't prep algebra here and find derivatives there. You first have to prep algebra, get it ready before you can find the derivative. Because as I said, the notation clearly tells you this is not the derivative, this is still y. This is still the function. Now that I'm ready, I will go and do all of those derivatives in one go. So I will say it's 2 over 3x to the power of, and careful again, 2 over 3 minus 1 is 2 over 3 minus 3 over 3, which is minus 1 over 3. Plus 2 times 3 is 6, x to the power of 2 minus 1, which is 1, but I'm not going to write that 1. And then this one we've discussed before, that's just going to be minus 4. But you could again just have gone and said 1 times negative 4 is negative 4, and then that's going to be x to the power of 1 minus 1, which is 0, and x to the power of 0 is 1. So that's why I can write it out like that. And then again, just good habits, we're going to move that negative exponent to make the exponent positive. And there's my answer. Now, in that same paper, they had this question. Now, this question again, spot the trick. Quite a few of them actually. There is a minus 1, so a negative exponent, and careful, that negative exponent is applicable to the entire bracket. Whereas over here, there's again a negative 1 and a negative 1. Now, the good news about these negative exponents is the following. We actually want normally that negative exponent, but you'll see just now there is going to be a little trick involved here. So first things first, we're still prepping the algebra, so this is still y. Please people, do not write dy over dx until you are ready to differentiate. So I'm going to write a fraction down because this entire bracket needs to move into the denominator position because of that negative exponent. Then over here, I'm going to write this out saying x to the power of negative 1 is 1 over x. And there's a good reason why I'm doing this. And I'll explain that just now. And this one is then going to be 1 over pi. And the reason I had to do this was because now you will notice I need to simplify this particular fraction. Because not only do I have that negative exponent problem, I now have the problem where it's a quotient. It's the top divided by the bottom, and we've spoken about this before. I cannot find the derivatives of products or quotients. There is a rule for that, but we only teach that to AP Maths, and they only teach that to you at university level mathematics. So for us, we have to simplify these fractions. Now for the AP people, if you are watching this video, you are completely and totally allowed to use the quotient rule there if you want to. That's completely acceptable if you know how to use the quotient rule. The rest of us, we are going to have to go the long way. Now, in order to do this one, I'm going to have to go and say it's the fraction at the top, which, if I need to simplify it, I need an LCM of the denominator. So I need to say the LCM of the denominator is pi times x. And then, because I need to multiply there by pi to get to that denominator, I will have to say 1 times pi is equal to pi. Plus, there I need to go and change that denominator to pi x. I need to multiply by x, I need to multiply by x, so this is going to become plus x. So I've now gone and simplified this top fraction, and it's going to be the top fraction divided by the fraction, well, in this case not a fraction, divided by the expression at the bottom. So it's going to be my numerator, simplified, divided by my denominator. I will then go and say it's pi plus x over pi x, and here I will change my division to multiplication, which means I need to change that to the reciprocal, which we call normally tip and times. I know lots of teachers prefer not to use the words tip or times. It's saying that if I change this to its inverse operation, I just need to make sure to change this to the reciprocal. And hopefully you'll notice, excellent, there I've got a common factor, so I can divide that away. And then eventually I've got 1 over pi x. Now unfortunately I'm still not done. I still haven't been able to find the derivative because I've just been simplifying algebra, but I'm almost there. And what I can do now is I just need to move that x out of that denominator position into the numerator. And to do that, I am going to leave this as 1 over pi and only move x into my numerator. And the reason for that is simply because a lot of people like to move these constant values into the numerator. But that actually becomes confusing because then a lot of people don't spot that the actual coefficient there is 1 over pi. And remember, we need to multiply the exponent by the full coefficient. So it's actually just easier to leave that coefficient as 1 over pi and just move that independent variable into the numerator position. Because now finally I can indicate dy over dx. I'm ready to use these differentiation rules. And I can say it's minus 1 times 1 over pi, which is minus 1 over pi, times x to the power of, and please remember, make that exponent 1 less. So minus 1 is minus 2. Now, again, good habits. We're going to go and say it's therefore minus 1 over pi x squared. But again, if you leave it like this, they generally don't have a problem with that. They're generally okay with you leaving it like that. Good. Continuing with past paper problems. Now, in this particular one, which is from the Department of Basic Education, the November 2018 paper 1, they say determine dy over dx if, and then they give you this. Now, this is again a Joshua method one. Okay, I kind of get it, but how can they complicate it? Now, the way to complicate this one particularly has to do with the fact that every single one we've done so far was in the format y is equal to, and then the x's appeared on the other side. But this one is what we call implicitly defined. Implicitly defined means the x's and the y's are mixed together. So whenever you see one of these that are implicitly defined, before I do anything about that derivative, again, I've got to prep the algebra. And in this case, I need to prep the algebra by making y the subject of the formula. Or else I can't use my rules. So I need to make y the subject of the formula. And this is back to grade 10 literal equations. So in grade 10 literal equations, it pretty much means solve for y. Now if I want to solve for y there, you should notice these are not like terms, so I can't subtract them. But I can factorize. So I take y out as a common factor, and I have x minus 1 left over there. Now, I know what's going to happen next, so I know it's probably a good idea to factorize this expression on the right-hand side. And the reason it's probably a good idea is because to get y on its own in the next step, I'm going to divide both sides by x minus 1. So because I'm expecting that I'm going to have a fraction that I need to simplify, I'm going to go and factorize by taking 2x out as a common factor, and that's going to leave me with x minus 1. Because if I now go and on both sides, I divide by that x minus 1 to get y on its own. So there I divide by x minus 1, there I also divide by x minus 1. Then you realize why it was actually a good idea to do this factorization. Because now over here, x minus 1 divides into x minus 1, and I'm left with y, which was the goal. And over there, x minus 1 divides into x minus 1, and I'm left with 2x. Now, this then explains also why they gave you a restriction over there. Why did they tell you x is not equal to 1? Because if x is not equal to 1, then it's okay if I divide by x minus 1. Because x minus 1, if x is equal to 1, would have been 0. And please remember, in mathematics, we cannot normally divide by a variable. And the reason we normally can't divide by a variable is because we could be dividing by 0. But in this case, because of the restriction they gave us, we didn't divide by 0. So all of that, again, we still haven't found the derivative. We've still just been simplifying the algebra. So now we're ready to say the derivative dy over dx is then equal to 2. So all of that effort just to get a derivative of 2. So I think again and again and again you'll see the derivative is not the difficult part. It's the algebra that I need to simplify that make these some tricky. Okay. Another example, this one is from the IEB March 2018 paper 1. So again, that's a supplementary paper. Now, what makes this one different than the previous ones we've done is they don't ask for f accent of x. In other words, they don't ask for the derivative in terms of x. They ask for the first derivative where x is equal to 2. Now, we'll get to that a little bit later, but if I want to get the first derivative where x is equal to 2, I do first need to get the first derivative of f. In other words, I need to get f accent of x. So before I worry about that too, I'm just going to go and I'm going to find the first derivative. So as stated before, you cannot find the derivative if you have a quotient. And how do we simplify fractions? First, factorize fractions. So first things first, I've got x as a common factor. So I will find that x as a common factor, and I'm left with x squared minus 2x minus 3 over x minus 3. Now, that gives me a trinomial, so I'll factorize that as well into a binomial times a binomial, which is going to be x times x, 3 times 1, and it's going to be minus 3 and plus 1 to get that minus 2x. And yay, lo and behold, that was excellent news, because now I can divide the x minus 3 into the x minus 3, which leaves me with x times x plus 1. Now, again, I'm not ready to find the derivative yet. Please notice this is all still fx. I haven't done any of the differentiation rules. This is still fx. I'm not ready yet to find the derivative because now I've got a product. So now I first have to multiply that x, so do the distributive law, saying it's x squared plus x. And only now is this in a format where I can find the derivative. So I indicate this is my first derivative of x, which is 2 times 1, so 2, x to the power of 2 minus 1, which is 1, and then in this case, it's just plus 1. So that's my first derivative. But I haven't finished the question. I haven't answered the question, because the question didn't ask for f accent of x. It asked for f accent of 2. So this, people, pretty much, it's a substitution. And it's specifically telling me substitute 2, not into fx, substitute 2 into the first derivative. So now that I'm ready, I can say the first derivative, where x is 2, is equal to that particular function, 2 times 2 plus 1, which is equal to 5. Now we'll get to this a little bit later. We'll talk about the importance of this, but for now that was just a notational issue, understanding what they wanted you to do. Now, to finish off this particular video, I just want to reiterate, because I keep on saying again and again and again, before you differentiate, there's lots of algebra to be done. So before you can even think about using your differentiation rules, you need to go and you need to look at the algebra of the problem. So I've just given you a couple of tips here, specifically, which is kind of like a checklist. So this could potentially be called the Michelle method. Here's your checklist before you differentiate. Simplify. Products need to be expanded. You need to multiply. If there's a binomial times a binomial, you need to FOIL it. You need to work that out before you can use your differentiation rules. Quotients. So fractions need to be simplified. Now this one can either be simplified by saying it's the first term divided by x minus the second term divided by x, or you can take x out as a common factor and divide it away. There are two options there. But simplify products, simplify quotients before you employ your differentiation rules. Sometimes, in order to simplify the fraction, you need to first factorize the fraction. So this one will be the difference of cubes, and then that will divide into the bottom, and then you can go and you can simplify and find the derivative. Next, write any surds as rational exponents. So this one you're going to write as x to the power of 2 over 3 before you can find the derivative. And then very important as well, write any independent variables in the denominator. So in this case, x is in my denominator as a negative exponent. But I did talk to you guys about this, just to state that again, when I go and I move that x to the power of 3 into the numerator, please don't move the 5. Rather leave the 5 over there and go, it's x to the power of negative 3. Why? So you have the coefficient there, because remember you're going to multiply that exponent by the coefficient, and it's just easier if you leave that coefficient in that fractional form rather than doing this. This, people, very bad idea, going 5 to the power of negative 1, x to the power of negative 3, because now you have to multiply negative 3 by 5 to the power of negative 1. So I would not suggest doing that. This is just simpler to do. So thank you for listening, and I will talk to you again in the next video.